Hi, my name is Mohit. I'm a third year undergraduate in the Department of Physics, IIT Roorkee, and I'm going to be talking about the discrete Fourier transform and its applications in image compression. So I just want to start off with a brief summary of what the discrete Fourier transform is and how it works. So the standard Fourier transform allows us to express an analytic function as a combination of sine and cosine waves of different frequencies. And the discrete Fourier transform kind of works in a similar manner, but instead of a continuous function, we have a set of data points. Now, this data is usually expressed as a vector or a set of vectors, and we want to express these vectors as a sum of sine and cosine waves with increasing frequencies. And these frequencies are given by omega n as given here, and where n is the number of points that we are operating on. The exact formula for the discrete Fourier transform is given right here, and there are two things to note here. The first one is that what the DFT essentially does is it takes in a vector and it transforms it into another vector, and the second thing is that all of these transformations, as seen in this formula, are linear in nature, which means that the DCT can be expressed as a matrix. A matrix that you simply multiply with your data vector and you get a vector of Fourier coefficients. This comes with two advantages. First of all, it's computationally inexpensive, and secondly, what this allows us to do is we can also express the inverse transformation, which is the inverse inverse DFT, as simply the inverse of this matrix. So what does this matrix actually look like? Well, if we just look at the formula, we can easily make out what the matrix would look like. So in general, like parametrically, the ij element, the element at the ith row and jth column is given by omega n to the power I cross j, I into j, if I and j were to be zero indexed. Here's some sample MATLAB code. Well, I'm actually using Octave. Yeah, but this code is pretty easy to understand as well. So what I'm essentially doing is n here is the initial data vector here is basically just a 1000-dimensional column vector filled with all ones, and then I just compute the corresponding omega, and then I initialize an empty DFT matrix and iterate through the entire matrix and populate it. And here you can see the output as well. Now that we've implemented DFT once, from this point onwards, I'll be using MATLAB's inbuilt function FFT, which stands for Fast Fourier Transform. It essentially does the same thing as DFT, but it's slightly more optimized. The only difference between DFT and FFT is in this step here. Like, instead of iterating through the entire matrix and populating each cell individually, which is essentially an O of n square operation, an operation which essentially takes O of n square complexity. What the fast Fourier transform does is it generates a vector mesh of I minus 1 and j minus 1, and then it simply raises omega 1 to that power. So the complexity is basically reduced from O of n square to O of n log n. Yeah, but what does all this have to do with image compression? Well, interestingly, the answer lies in the fact that not all of these waves that make up this vector have equal significance. So, for example, so what the Fourier coefficients essentially denote is they denote the amplitude of a wave of that frequency in the resulting vector, right? So in a way, we can think of the Fourier Fourier coefficient of a wave as its contribution to the image, so to the vector. So so I guess it's safe to assume that those with lower Fourier coefficients have much lower contributions. So in theory, I could drop out some of these waves with low Fourier coefficient values, and my image would more or less remain the same. So the complete process looks like this. You take the original uncompressed image, you apply the fast Fourier transform and to convert it into the frequency domain. Then you apply a threshold, which basically means you agree on a threshold value, and then you drop all the waves which have an amplitude below this threshold. This leaves you with with a much less smaller number of frequencies to store. Then you which essentially reduces the amount of data that you need to store the image. This is what this is where the compression part happens. And then if you want to see the compressed image, you can simply apply the inverse Fourier transform on this on these compressed frequencies and get back a compressed image. The complete code sample here looks the complete code example for this looks is right here. So yeah, so another question that arises at this point is that so far what I explained about the discrete Fourier, the discrete cosine transform and the fast Fourier, the discrete Fourier transform and the fast Fourier transform, that they're supposed to operate on vectors. But an image, which is a collection of pixels, is essentially a two-dimensional matrix. So how do you apply a fast Fourier transform to a two-dimensional matrix essentially? So the way you do that is you apply fast Fourier transform to each of the rows individually, and then you take this new matrix and then you apply fast Fourier transform to each of the columns one by one. And this is how the two-dimensional fast Fourier transform works. Fortunately for us, MATLAB also has a built-in function called FFT2, which is the two-dimensional fast Fourier transform for this. This code, yeah, so this code is pretty self-explanatory as well. You read the image, and the image that I was working on is a 300 pixel by 300 pixel image, but it's an RGB image, which means that there's three channels on it. There's the red channel, the green channel, and the blue channel, which means that each pixel needs 3 bytes to be represented. So each pixel is gonna have a value between 0 to 255 for each of the 3 colors. So to keep things simple, I've converted it to grayscale, which means that each pixel now only needs 1 byte to be represented. So each pixel is essentially just an 8-bit number between 0 and 255. Then what I do is display the original image. Then you apply the fast Fourier transform to convert it to the frequency domain. And then what this 0.001 does is what this thresh declaration does is this means that the threshold is 0.1% of the maximum Fourier coefficient within that matrix, which means that any wave whose Fourier coefficient is less than 0.1% of the maximum Fourier coefficient gets dropped out. It gets zeroed out. Then I simply just compute this index matrix. So the IND matrix will have values will be populated by zeros and ones. One wherever the Fourier transform, the Fourier coefficient is above the threshold, and zero elsewhere, and zero everywhere else. And I just basically take a dot product with this matrix to zero out those values below the threshold, and then I apply an inverse fast Fourier transform to convert my image back to the pixel space, and then I display that converted image. And this is what it looks like. So this the second image contains 64.36% contains 64.36% of the pixel count of the original image. And you can kind of see the grain beginning to appear, but it more or less looks the same. Yes. So this is this was how fast Fourier transform is used in image compression. This is actually quite close to the core functionality of the JPEG compression system, the JPG/JPEG compression system that we use every day, except that the only difference is that it uses discrete cosine transform, which means you only consider the real part of the Fourier transform. But yeah, this is something that has a lot of real world implications. And that's about it from my side. Thank you.